Welcome, friends. In this section, we will come to see another topic, and that is the fault or short circuit MVA. So, we will see what is a short circuit MVA and what is the relationship of short circuit MVA with the percentage impedance of a transformer. So, why we want to calculate the short circuit MVA. So, first of all, if you see a transformer, so if I draw a transformer, so this is a simple single phase transformer and it is supplying a load here. So in this case, you can see the current is depending upon the load impedance ZL, for example. If the impedance is reducing, the line current or the load current will increase. But what happens if there is a fault on the line? For example, if there is a phase to ground fault on the line, then you can see easily that the load impedance will be completely bypassed in this case. And you can see, for example, if the neutral of the transformer is also grounded, so the current will flow back to the winding and this impedance is completely bypassed. So here you can see this is the loop or the path of the fault current IF. So in this path, the current will be limited by, so you can see the IF will be equal to transformer low voltage side LV voltages divided by impedance of the transformer. Okay, so this is the impedance of the transformer plus the impedance of the line and the earth resistance. Okay, so this is all in case of phase to ground. But what will happen if there is a short circuit on the terminal? There is a worst case of the short circuit. In case of worst condition is when there is a short circuit on a three-phase terminal of the transformer. So of the three-phase, all the three-phase of the terminal of the transformers are short-circuited. So in this case, you can see the current will be flowing through all three phases, and only thing that is limiting the current here is the impedance of the transformer itself. So this impedance, we can call it as a Z percentage impedance. So here you can see this is 12.5 in this transformer. So as a thumb rule, if the voltage, if you will see this, if the voltage of the transformers are increasing, for example, if there is a transformer 132 by 11 kV, the percentage impedance here you can see is 12.5%. So if you have another transformer that is 11 kV by 400 volts, for example, this is a distribution transformer, you will see the percentage impedance is dropping to 5% or 4%. And if you see another transformer like 220 kV by 132, the percentage impedance will be more higher. For example, it will be 18% to 20%. So if the voltages are increasing, the fault levels are also increasing, and we want to control the fault current in that case. So we can control the fault current by increasing the impedance of the coil itself, because this is the limiting factor in case of fault on the terminal of transformer. And we are designing the transformers at the worst possible faulty condition, and that is normally three-phase short circuit. So this is one case. And secondly, while doing the setting calculations, we have to make sure that in case of short circuit, our differential protection should be able to pick and trip in case of a in-zone fault. So here you can see the impedance, percentage impedance is 12.5 volts. So if you want to calculate the fault MVA, so we know that we have already know the formula of S is equal to √3 V into I. So this is the formula for normal calculations for the transformer, that is to calculate the full load current of HV side and LV side. But the same formula is also applicable for short circuit calculation, as short circuit is equal to √3 V into I. So how you have to find out the short circuit MVA of a transformer? So the formula is quite simple. So you have to divide the MVA of a transformer. So this is MVA, 100 MVA, divided by the percentage impedance, which is, you have to divide it by 100, which is 0.125. So then short circuit MVA will be coming as 100 divided by 0.125. So it's equal to coming as 800 MVA. So you can see here, this is 800 MVA. Here is a short circuit MVA of a transformer. MVA short circuit. So what does it mean? So it simply means, let me make another. So it simply means, now we have calculated S here is equal to 800 MVA, and this is the short circuit impedance of a transformer. So this is short circuit impedance. So this is 132 kV by 33 kV transformer. So if I want to calculate short circuit level at the low voltage side, I have to use the same formula. This is equal to under root 3 V into I. So then I want to calculate I short circuit current at the low voltage side, then it will be equal to 800 into 10 raised to power 6 divided by under root 3 divided by 33 into 10 raised to power 3, and that's 3, 6, it will be 10 raised to power 3, so it will be coming like 800 multiplied by 1000 divided by 1.732 divided by 33 divided by 1000. So it's coming as 13.996, or we can see it's equal to 14 kilo amperes. So you can see here the short circuit level at the low voltage side is coming as 14 kilo amperes. So it means that if you are supplying 132 kV at the HV side and the LV side is short circuited, then this much of the current will be flowing through the low voltage side. So in the same way, if supplies at the low voltage side and HV side is short circuited, I short circuit HV, this is LV. So HV, just we have to multiply, you have to change here 800 K divided by under root 3 into 132. So it will be equal to 800 divided by 1.732 divided by 132. So it is almost equal to 3.5 kilo amperes. So this is the case when LV side has a source and HV is short circuited. So in this way, you have now calculated the fault current in case of HV fault and LV fault, and you have now understood the relationship between the percentage impedance and the fault MVA and fault current. So this is the basic formula to do the calculation. So when we are doing our setting calculations, we obviously will be using this formula to do our calculations. Thank you very much. Welcome back. In this section, we will calculate the high voltage side through fault current at plus 10% tap position and minus 10% tap positions. So in the last session, we know how to calculate the fault currents at the HV side and at the LV side. So one option of the calculations for the fault current at HV and LV side is to find out the short circuit MVA, and then divide, you first of all you have to find out the MVA of the transformer, divided it by the percentage impedance. So you will get the short circuit MVA, and then if you have a short circuit MVA, then you can again use the formula under root 3 V into I, and then you can calculate the short circuit current at HV and LV sides. So this is a one way of the calculations. Other way of the calculations here is if you know the full load amperes, full load amperes that we know I already calculated. If you divide this full load amperes by the percentage impedance, then also in this way you can calculate the fault current through fault short circuit current at HV and LV side. So this is basically the another method of the calculations. So here you can see, if you have we know that the HV side full load ampere here is I full load ampere is equal to HV side is 437.4. so if you divide it by the percentage impedance 12.5%, that is 125, then you will be getting the short circuit MVA. So you're dividing it by the percentage impedance in order to get the through fault current or short circuit current. So just you have to divide 437.4 divided by 0.125. So again you will get 3499.2 amps. So in this way you can also do the calculation, which is a simpler way of doing the calculations and finding out the through fault current. So what is a through fault current? Actually, if you consider a three-phase transformer, so if for example this is a three-phase transformer, that is star delta, and if there is a fault on the line, for example, or the terminal of the transformer, then current will flow at the LV side and HV side. This is called as short circuit current, and this current will be called as a through fault current or short circuit current of the transformer. So we have here shown how you can calculate the current for the high voltage side. In the same way you can calculate the current for the low voltage side. So if I calculate the current for low voltage side, it will be equal to I short circuit low voltage will be equal to I full load amperes divided by percentage impedance, and then it's equal to 1749.5 divided by 0.125, and that's equal to 1749.5 divided by 0.125, so it's equal to 13,996 amperes. So this is one methodology. So here we'll calculate the through fault current at the extreme tap position. So when you can see when the current when the tap is at plus 10, which is extreme plus, so when the voltage are at the highest side of the HV side, so you can see full load ampere plus 10% divided by the percentage impedance using this similar philosophy as we just have learned. So you have to divide, this is the full load ampere, you have to put the full load amperes here, okay, and then divide it by 0.1250, and then you can get here simply the full load current. So here what they have done, this is the formula that they are using here, is S is equal to under root 3 V into I. So I here is equal to S, which is 100 MVA divided by under root 3, and this is the voltage at tap when the tap is plus 10%, which is 145.2. So at this step the full load the short circuit current is equal to 3181 amperes. So in the same way we will calculate the short circuit current when the tap is at minus 10%. So here you can see again you have to put the full load amperes, okay, at the HV side, and then you have to make minus 10%. So using the same formula as equal to V into under 3 V into I, V here we have chosen at minus 10%, okay, that is 118.8 kV, and you have to divide it by percentage impedance, which is 0.125, so you will get these two currents. So now we have done the calculations of through fault or short circuit current at plus 10% tap and the minus 10% tap. Thank you very much.